recording.
Oh, thank you so much, Saurav. So, hello, folks. My name is Sayan Ghosh, and I'm a computer scientist at Pacific Northwest National Lab. And welcome to the second session. And in this session, we are going to have three presentations, and two of the presentations will be from the technical program, and the third one would be an invited talk from IL Labs. So for the two presentations, so you are in the network hardware session. So for the two presentations, we will discuss, we have an exciting talk. So I'll start immediately, the first one. So the first presentation, paper presentation is from Saeed Fathololoumi, and I'm going to start the video and introduce him momentarily. So Dr. Saeed Fathololoumi is currently a principal engineer at Intel, where he is leading the Silicon Photonics integrated circuit design and technology development for co-packaged optics products. And he has over 15 years of experience in developing technologies for novel optoelectronic devices and systems. He has previously worked at Elenion, Mellanox, Coursera, and National Research Council of Canada. He obtained his PhD in EECS from University of Waterloo and has over 50 publications and 17 US patents. And since we are running short of the time, maybe we won't have time probably for a live Q&A. So please move your questions to the dedicated Slack channel, and I will start the video now.
I cannot hear the audio here. So.
Did you say the audio is not there?
No, I cannot hear it.
Okay.
It's rough.
Saurav, can you confirm if that is the case? Or Rohit?
Yeah, it looks like we're having the same issue as the previous session. So
Okay.
I don't know.
Thanks
I don't
for
know what
letting me know.
I don't know what the fix was, but
So I'll stop share and try again. Sorry for the issues, folks. This is the first time we are using, Zoom events. So, yep. The same issue. We don't see the options below. They are grayed out. Folks, please hang on. We are having some technical difficulties. We'll soon get it sorted. Let me try one more time. Can you hear?
no. Not yet.
No, not yet. Okay. All right, I'll stop share.
Rohit, did you make any changes last time?
No, I didn't actually make any changes last time. I don't know. I thought it started working from some changes that you had made, but I guess not.
Can you make Sayan host since he's trying to hear?
All right. I've made Sayan the host now.
Okay, and I will give it a try. Nope, I still don't see the options.
I/O bandwidth and the power of the I/O becomes a bottleneck for getting more performance. So this requires the I/O bandwidth scaled also with the Moore's law. In addition to within processor interconnect, the recent AI and the machine learning type applications have required high performance computing by utilizing massive number of processors and memory. Because of that, the off-chip I/O bandwidth became important. As the bandwidth of off-chip I/O increases, the total power consumption required for interconnect also increases, as we can see in the top left graph. The lower graph from DARPA's Dr. Keeler also shows that with the current rate of power scaling for the I/O, basically the I/O for the off-chip data, the power for the I/O can surpass the actual computation power in coming years. Another limitation for AI and machine learning type application is the actual bandwidth and the latency of the interconnect. The middle graph here shows that the bandwidth and latency of the I/O improves for a benchmark that has lower latency and higher bandwidth. And because of that, the utilization of the total available nodes increase at the as the node count increase. Lastly, due to the limited shoreline of the processors and basically the ASIC that we want to do the I/O, the bandwidth density also needs to improve alongside with the other metrics. Currently, the electrical I/O is struggling to meet these requirements as shown in the lower left graph because of the power requirement. The optical compute interconnect, or as we call it OCI, is expected to break these barriers and enable high bandwidth, low power, and high density I/O for the future computation. These panel graphs illustrate the architectural differences between the electrical I/O and the OCI within the high performance computers and accelerators. On the left panel, we can see that the processors are connected through electrical I/O that's limited to tens of inches, and only limited number of them can be integrated within the same board. In order to scale the computation nodes beyond the board, it's expected to go through a network card, basically the network interface card. Current state of the art for such I/O is basically a total data rate and bandwidth of around half a terabit to 2 terabits per second, and a shoreline of around 100 to 500 gigabit per second per millimeter, and energy efficiency of 5 to 10 picojoule per bit. However, on the right-hand side, we see the OCI kind of architecture and topography. It integrates the actual optical I/O right next to each of the computation nodes or any of the resources. This allows for high bandwidth and low power connectivity between nodes that can be physically separated up to hundreds of meters. OCI is expected to provide a total data rate of more than 4 terabit per second. It can be 4 to 64 for a few years to come, terabit per second. Bandwidth and shoreline density of 400 gig to 2 terabit per second per millimeter, and energy efficiency of less than 4 picojoule per bit, while providing connectivity of up to hundreds of meters. Such architecture can be enabled by fully integrating PIC, EIC, and advanced high-density packaging. This also has been known in industry as co-packaging optics, as you might have heard in the Ethernet world, and for Ethernet applications. In those applications, the basically optical chiplet sits next to the ASIC and are co-packaged together. But in general, in order to scale the optic bandwidth density, we need to integrate the optics closer and closer to also have the lower power and higher density. In this slide, I like to distinguish between these two types of co-packaging optics or CPO, between the Ethernet basic applications on the left column or middle column here, and the OCI applications. The Ethernet CPO replaces the pluggable optics and is used for switch-to-switch or NIC-to-switch kind of links. It requires to cover up to 2 kilometers, in some cases 10 kilometers, based on the standards for the DR or FR standards from IEEE. It's not latency sensitive, so it has 100 nanosecond plus time of flight kind of requirement. So it can use this, strong effects like KP and PAM4 modulation to increase the bandwidth for 100 gig and 200 gig lanes. The host side interface is also governed by IEEE and OIF standards. On the other hand, for OCI, this kind of technology replaces the current copper-based SerDes, such as PCIe or CXL. It's used for computer fabric scale-up and scale-out, as well as the resource disaggregation and pooling. Its reach is basically expected to be up to 100 meters or so, and it's very latency sensitive. So the latency should be less than 10 nanosecond plus time of flight. Although there is no current standards, while there's working groups right now being formed across industry, and we expect to get some agreement across industry on these. But because of the latency requirements, it's expected that the NRZ type of modulations are used, and very light FEC or no FEC is basically used in this kind of things. In order to provide a high bandwidth density, dense WDM links are usually proposed. They're covering from 16 gig up to 64 gig are expected. And on the host side, the UCIe is the basic UC type interface is being adopted. In general, I can say that different requirements between these two applications, they drive different architectures and solutions. This slide shows Intel's vision for the OCI. We keep basically the electrical and photonic technology nodes separate in order to be able to use the best available process and PDK for each of these ICs. 3D packaging, hence, is required to integrate these two dies together and also keep low loss and high bandwidth signal integrity between these two dies. The EIC include all the functions needed to communicate with the host, gearbox, and signal to use the gearbox from the host side to line format, line rate, and as well as driving and controlling all the optics and photonic components in the picture. The photonic IC or PIC also integrates all the transmit and receive and fiber coupling components on the same die. We integrate lasers and SOAs and basically for amplification within the same die, which allows us to keep power consumption low while having high quality link with the self-contained transceiver chip. We are projecting to achieve ultra high bandwidth up to 1 terabit per second per fiber and reach up hundreds of meters, as I indicated in the last slide. These kind of metrics are order of magnitude better than electrical I/O. We can achieve shoreline density of more than 4 times better than EIO and energy efficiency of below 3 picometer, which is 65% of the PCI Gen 6. The latency of these devices are expected to match the EIO kind of applications of 10 nanometer plus time of flight, which is kind of required for compute scale out and resource pooling applications. In order to develop such platform, a scalable and high volume silicon photonic infrastructure is needed. At Intel, we integrate the photonic devices on our 300 millimeter wafer platform using advanced CMOS manufacturing process. We also integrate the gain material and lasers on the same platform using Intel's hybrid laser technology. But also another piece of key capability to have to enable a high volume optics manufacturing is to have a wafer level testing and wafer level kind of burning and evaluation of the devices with all the lasers and SOAs in place so that we can determine all the KGDs or known good dies on the wafer level that is required for the high volume manufacturing. In order to achieve a low power, high bandwidth density and low cost, it's important to integrate all the photonic components within the same die. So for power density, we use on-die lasers and amplifiers. Our solution generates the light in the hybrid mode and output is already within the silicon wafer. External light sources require 2 additional coupling to couple the light into the fiber and then into the photonic die. Additionally, they require use of PM fiber that can complicate the assembly process and increase the cost. We also use efficient ring modulator with low drive voltage that can enable advanced CMOS node to bring down the EIC power. Also, in order to achieve the high bandwidth density, the same compact ring, micro ring modulators are integrated within the platform. We also integrate high-speed germanium PD devices to enable integrated TX and RX peaks and additional. And also we additionally we do a die stacking and do the 3D packaging for dual-sided packaging that's being developed to accommodate these kind of OCI architectures. On the cost side, as mentioned previously, integrated lasers enable low-cost integration of the light source. We have also integrated V grooves to enable passive optical alignment of large fiber arrays. Lastly, we designed our photonics to be polarization drivers, enabling low-cost single-mode fiber grooves. This cartoon here shows the architecture of our OCI PIC. For the first gen, we use 8 lasers, 8 laser wavelengths at 200 gig grid, matching the CW, WDM kind of also standard industry MSA. Then we mux and split them into 8 different buses, each with 8 ring modulator arrays intended to log to each of the 8 wavelengths. Consequently, we amplify a signal before coupling to the fiber. On the receive chain, after coupling to silicon photonic die and do the polarization management, we amplify the signal, and then we use the interleavers to separate the odd and even channels to lower the crosstalk penalty. And eventually, we use ring add drop filters to demux each wavelength into separate high-speed journeys. Our lasers show basically a SMSR of more than 50 dB, ring of below minus 45 dB per hertz. We can achieve more than 25 milliwatts of power within the silicon waveguide at ADC. And last but not least, they have shown to be very reliable. From the millions of these devices that we have sold using this technology, we have seen actual fit rate, field fit rate of less than 2, which shows that these lasers and displays are very, very reliable. Also, we integrated micro ring modulator arrays. They're designed to passively match the laser grid, the Q of around 4.5K and the phase efficiency of less than half a volt centimeter, which is going to allow us for having a low swing voltage drive requirement from the EIC side. The SOAs also are integrated. They have a gain of more than 9 dB and PSAT of more than 12 dBm. We also, as I mentioned, integrated interleavers. At the interleavers, they're very low loss of less than half a dB, and they have a total crosstalk of way less than -10. Yeah. Finally, we, as I mentioned, we integrated the demux add drop filters that show loss of less than 1 dB, and they have a bandwidth of around 5 meters. We integrated these devices into a single PIC die using Intel's high volume silicon photonic platform and process. The die has 8 lambdas on each of these 8 buses, with each channel running at 32 gigabits per second NRZ. This makes the total bidirectional bandwidth of this die to over 4 terabits per second, or half a terabit per second per fiber. We have basically the chip in our lab right now, and it has turned on, and we can see we have all the lasers operating together at around 13 nanometer within the 200 gigahertz grid. We tested these devices at high speed as well. So we basically kept all the lasers on, and we turned basically 2 additional aggressors on each of these basically devices. The device showed a very open optical eye with more than 5.4 dB extension ratio and bit error rate of below 1 in -50, which is critical, this kind of error-free operation to enable low latency link. Additionally, if we basically at 32 gig, if we count all the powers at the end of line, worst case temperature for these kind of devices, including lasers and amplifiers, it's going to consume less than 1.75 picojoule per bit. For the next generation, we have few scaling vectors to double the bandwidth between each generations. The current architecture provides unidirectional 0.25 terabit per second fiber, as you can see on the first point on this graph, per fiber. The next generation is expected to double the data rate to 64 gig. After that, the number of wavelengths can double to provide scaling. Another vector is to use the state of polarization mode for the next bandwidth scaling. And eventually the data rate can go up to 128 gig, and the number of wavelengths can increase to 32 and 64 lambdas to provide further scaling in the bandwidth density. And technically can achieve beyond 10 terabit per second per fiber. But the main thing is that this application and the product requirement will drive the actual order and timing of these vectors and the intercepts. Just to give you a quick kind of glimpse into the future also, I covered the critical high-speed components in this slide for scaling the data rate. We have previously demonstrated the ring modulator actually in the OFC last year, operating at 128 gigabit per second NRZ with less than 2 volt peak-to-peak drive and extension ratio of 3.8 dB. It's important to note that the actual performance is limited by the test apparatus. The EO bandwidth of these devices measured to be beyond 60 gig at the operating point. The next device is the PD. On the PD side, we have also shown previously that our PD bandwidth are beyond 40 gig, and so their dark current is around 100 nanoamp in temperature and responsivity of 1 watt. So these, although this is most probably okay for the 60 gig, but for 128 gig, the further optimization of this component is expected to further improve the bandwidth and the performance. Okay, so lastly, to conclude, here I introduced the concept of OCI, which is optical compute interconnect, and reviewed the benefits in addressing the bandwidth and power bottlenecks. Also, I introduced the high-volume manufacturing-based silicon photonic platform and demonstrated the required IPs for the OCI architecture. The integrated peak performance was presented, showing that showed BR of below 1E-15 and shoreline density of around 0.46 terabit per second per minute. And the peak energy efficiency for 32 gig was 1.5 picojoule per bit, including the laser and the gain, but increasing the data rate to 64 gig, we expect to bring down the peak power to below 1 picojoule per bit. At the end, I'd like to thank all of the contributors, and I would like to basically take any question if there's a time, either live or through the Slack channel. Thank you very much.
Thank you very much, Saeed. So I see there is a question, and I will read it out to you. And folks, I would ask you to go to the Slack channel and post more questions. I know some of you are having problems with the Slack, and we are looking into it. The question is that maybe, I will read out one question, and after that, I will try to start the next video, and you can, answer the rest of the questions on the Slack channel. Saeed. So the question is this an internal interconnect or external fabric? One of the slides said PCI CXL alternative. So is it internal or on the motherboard?
So basically, that's more like a computer architecture type of question. So these devices, they are expected to sit close to any of the basically compute nodes or the resources, right? And the big beauty of it is that the fabric can be designed based on the different computer architecture, right? So they provide kind of optical I/O connectivity for these devices to basically scale up and scale out and kind of like helps disaggregation. But the specific of how it can be done, I cannot comment on that.
Thanks a lot, Saeed. I really appreciate you sticking around. And once again, big thanks to you for changing, for the flexibility that you showed, quickly changing the mode. And once again, I would like to deeply apologize for the technical issues. So the next talk is about the CPU interconnect Compute Express link, and the presenter, I'm going to play the video shortly, and the presenter is Dr. Debendra Das Sharma from Intel. And brief bio of Debendra. So he's a Intel senior fellow and a co-GM of memory and IO technologies in the data platforms and artificial intelligence group at Intel Corporation. And he's a leading expert on IO subsystem and interface architecture. He's a member of PCI Special Interest Group, lead contributor to the PCI specifications, co-inventor and founding member of CXL Consortium, and co-leads the CXL task force. He's a bachelor's in technology in computer science and engineering from IIT Kharagpur and PhD from University of Massachusetts Amherst, and he holds 160 plus US patents and 400 plus patents worldwide. He has many other accolades. He's been distinguished lecturer, invited speaker, panelist at the previous IEEE Hot Interconnect, Cool Chips, PCI SIG Developers Consortium, etc. So I'm going to play the video, and please let me know if you are not able to hear the sound.
There is no sound. Sayan.
Oh, there is no sound. Okay, I will try again. Share sound. Hopefully this is going to work this time. Apologies,
Greetings.
folks.
My name is Debendra Das Sharma. I'll be talking about Compute Express Link, an open industry standard interconnect enabling heterogeneous data-centric computing. The agenda for today is as follows. We'll start with an introduction. Then I will delve into CXL 1.0 and CXL 1.1 interconnect architecture. We'll talk about CXL 2.0 next. Then we'll talk about CXL implementation and some results that I have. And finally, we will conclude. We see continued proliferation of cloud computing, more widespread deployment of AI and ML, and cloudification of the network and edge. These industry megatrends are driving the demand for faster heterogeneous data processing, as well as more memory bandwidth and more memory capacity. The picture on the left shows the system level view with PCI Express only. Memory attached to the CPU, such as DRAM, is mapped as coherent memory, and their data consistency is guaranteed by hardware. But memory attached to the PCI Express device, even though it is system mapped memory, it is a memory mapped IO space and it is uncached memory. Accesses by the CPU is typically cacheable accesses, whereas accesses by the device, because PCI Express is a non-coherent link, is through non-coherent accesses known as DMA, direct memory access. And fundamentally, the CPU is the one that merges the two worlds so that data consistency is maintained between these two different domains, which are load store interconnect. And that model really works well for a vast range of applications. We want to preserve that, but with the new set of usage models that are coming up, we want devices to operate in a finer grained sharing of data with the CPU. They want to be able to cache the system memory, and at the same time, memory that is attached to the device can be also cached by the CPU. That way they can much more collaboratively work at a finer grained level without having to move entire data structures back and forth. And the other side benefit of this is going to be that you can use that for memory expansion, as we will see later. So CXL enables the picture on the right while preserving the goodness of the picture on the left. The picture here on the left shows the amount of number of cores versus how much memory bandwidth per core we are getting over time. This is data from Meta. And the picture on the right shows the price per gigabit of memory. As you can see, it has flattened out. So what these trends mean is that as we go through this increasing demand for compute, the demand on the memory bandwidth is not slowing down on a per core basis. You basically need to feed each and every one of those compute elements, whether it is the mainstream CPU or a bunch of heterogeneous compute. That's on an upwards CAGR, whereas the memory bandwidth per core is coming down, not because we are not adding more memory channels or not because we are the memory frequency is not increasing, the DDR frequency, those are increasing, but they are not able to keep pace. The amount of channels, if you increase the number of memory channels, those are very pin inefficient, and we are really running up against pin limitations at a package level. And as these computing packages become more and more powerful, they also need more and more memory. So what's happening is that the cost of memory as a percentage of the system cost is increasing tremendously. So these are the two sets of challenges that we have. And where is the computation demand going? It's exploding exponentially. And in order to meet the computational demand, we need to do heterogeneous processing. At the same time, we need to also solve the memory problem, and Compute Express Link is designed ground up to address these challenges, as we will see. CXL is built on top of PCI Express infrastructure and leverages PCI Express. It uses PCI Express alternate protocol mode and 128B, 130B encoding. It runs on PCI Phi at 32 giga transfers per second, though one can downgrade the speed to run at 8 gig or 16 gig. The native widths supported are by 4, by 8, and by 16, though in degraded mode we can run at by 1 or by 2. As a result, one can use PCI Phi for PCI Express or CXL, or even a proprietary CPU to CPU symmetric cache coherency link like Intel's ultra-path interconnect, as shown in the picture on the right. A standard PCI slot can have either a PCI Express card or a CXL card attached to it, as shown in the picture on the left. This enables customers the flexibility of choosing different mix or PCIe or CXL cards depending on the need that they have. Compute Express Link is defined ground up to address the challenges in the evolving compute landscape by making both heterogeneous computing as well as different types of memory efficient. It has three major aspects to it. CXL overlays caching and memory protocols on top of existing PCIe protocol. All the three protocols run on PCI Phi and channels, as shown on the picture in the right. CXL.io is the I/O part of the stack. This is almost identical to PCI Express. We use it for device discovery, configuration, register access, interrupts, virtualization, and most importantly, the bulk DMA with producer-consumer semantics. CXL.io is a mandatory protocol in CXL. CXL.cache protocol is optional for a device. It allows a device to cache the system memory in a coherent and low latency manner. CXL.memory protocol is also optional for a device. It allows the processor as well as other CXL devices with CXL.cache semantics to access the device attached memory coherently. This results in the converged memory as shown on the picture on the right. Latency is the second aspect. It's a critical component to ensure system performance for CXL. Especially once you have coherency and memory semantics, latency becomes super important. We are expecting latencies for CXL.cache and CXL.memory in the range of existing symmetric cache coherency links like our ultra-path interconnect or UPI. For a CPU load to use latency, we expect it to be significantly less than 200 nanoseconds, which would be, again, significantly less than a half for a comparable PCI Express access. The third aspect of CXL is it is an asymmetric protocol. Thus, the protocol flows and message classes are different between the host processor and the devices. That's a conscious decision to keep the protocol simple and implementation easy for devices. Host processors have their proprietary home agent functionality, which orchestrates cache coherency in the system, home agent is very dependent on the underlying microarchitecture. CXL just abstracts that caching functionality through a simple set of commands conforming to the messy, which is modified, exclusive, shared, and invalidate cache coherency protocol for simplifying the CXL.cache implementation on the device side. Similarly, memory access commands with built-in capability to store metadata such as directory is done for the simplicity of implementing CXL.memory. This way, memory devices don't need to understand coherency flows. This asymmetry is fundamentally what has helped us ensure backward compatibility without stifling performance or innovation, and at the same time making CXL really easy to implement across the industry. Here are some typical usage models targeted by CXL 1.0 and 1.1. There are three types of devices named as Type 1, Type 2, and Type 3 as shown in the picture from the left to the right. An example of Type 1 device would be a smart NIC or accelerator. It uses the I/O and caching semantics. The CXL.IO is used for bulk transfer, and caching is used for things such as advanced atomic support or things like PGAS ordering enforcement in a smart NIC. So instead of waiting for a read completion before launching a write on the I/O side, because PCI Express has a different ordering semantics than PGAS, the smart NIC can simply prefetch those cache lines out of order and complete them in the local cache in order, thereby getting huge amount of realized bandwidth across the link. Type 2 examples are GPGPU and dense computation, where all three protocols are used. Here the accelerator and host processors work very closely. There is no need to hand off the entire data structures and results. Only those that are used will be cached, and cache coherency ensures global data visibility. Last but not the least is the memory buffers, the Type 3 devices as shown on the picture on the rightmost. Given that SerDes is very bandwidth efficient per pin, we can use CXL for memory bandwidth and memory capacity expansion. This also enables heterogeneous memory, including persistent memory and multiple memory hierarchies, since the memory controller is with the device. Also of importance is that Type 2 can be deployed to some of the traditional memory type devices to deliver even more compelling value propositions, such as near memory compute. CXL is a FLIT-based protocol. FLIT stands for Flow Control Unit. The FLIT size is 66 bytes, which consists of a 64-byte payload and a 2-byte CRC. The 2-byte CRC guarantees 3-bit flip detection. Each FLIT is preceded by a 2-byte protocol ID, as can be seen in the picture, and that's used to distinguish between different protocol types, link management types, and there is replication built in within the protocol ID that guarantees triple-bit flip detection. The sync header that is shown in the picture can be bypassed for latency optimization, as that avoids a huge set of muxes. It also provides an additional 1.5% bandwidth. CXL.cache and memory transactions occupy one or more 16-byte slots, so they are naturally aligned to the FLIT of 64 bytes. CXL.IO uses the same TLP, DLLP transaction layer packets, data link layer packets as PCI Express. We just overlay that on the FLIT, and the 2-byte CRC is ignored for CXL.IO, as the TLP and DLLP in PCI Express has its own CRC. We just reuse that CRC. The FLIT layout on a by 8 link is shown here. As can be seen, given that this is 68-byte, the FLIT can end at a 4-line boundary and a new FLIT starts. So you can see that there is a sync header, there are a couple of FLITs that go on, and in fact the second FLIT moves to the next 128-bit, 130-bit block boundary. The third FLIT then starts in lane 0. So that basically ensures that we do not lose the bandwidth. Now let's look into the CXL.cache and CXL.mem protocols. For CXL.cache, we have 3 message classes. Each message class has its own independent flow control and crediting mechanism. The 3 classes are request, shorthand is REQ, rec, response, shorthand is RSP, and then in general the data, right? The 64 bytes of data that moves, whether it is with the request or the response. So those are the 3 message classes. There are 2 directions clearly. One is the device shorthand is D, and the other one is host, which is the CPU, shorthand is H. So the device to host side, you got the request category, and those are two types. So one is read for memory, and the other one is the write. And those translate to memory read and memory write, right? Memory read can be of different types, like read shared, read own, all of that. And there is basically those things result in the host to device side response, which is a GO, stands for global observability. Now from the host to device side, basically the request is snoops and different flavor of snoops, telling the device, snoop invalidate means invalidate this cache line up. Once you give me the response, snoop current means you can keep a copy of it as a snapshot if you want. And the corresponding response comes from the device side to the host side. RSPI means the device has made, didn't have the line, it's invalid, or it can be, RSPS hit SE, which means that it was in the exclusive state and you move to the S state, things of that nature. CXL.cache is primarily unordered with the exception of Snoop needing to push GO or global observability to the same cache line. The picture on the right explains it. In this example, device C issues a read share transaction. The home agent gets the request, sends a Snoop to B, maybe because B had the line earlier or had silently discarded it, or maybe the Snoop filter may not be precise, and B responds with an invalid response. B then follows up with its own read on to the same cache line. By the time it reaches the home, it has already sent the data with go to C. It then follows up with a Snoop invalid since B wants the line to be exclusive. Now the Snoop Go ordering requirement will enforce that C will first receive the Go and then it will get the Snoop. If they had gone out of order, then C would have responded with RSPI, and eventually then C would have later on received the Go and think that it had the line as shared. And in the meanwhile, B would have received exclusive ownership, and that would have resulted in a messy protocol violations. So that's the only ordering that we expect in the CXL.cache. And since the ordering is enforced, C responds only after invalidating the line and coherency is maintained. Here C may have used the data before responding to the Snoop, which would be fine. CXL.mem, it's a transactional protocol. It is directional. There are two message classes in each direction, and the direction are host, which is represented as M, and the device, which is represented as S, master and subordinate. So M to S request, things are like read, and M to S RWD is again another type of request, but those are the writes. So we separate them into two different message classes, and the response from the S to M side is no data response, like a completion, or a data response with data. So that's the CXL.mem, very simple stuff. Now let's talk about the second generation of CXL, which is CXL 2.0. It does maintain full backward compatibility with CXL 1.1 and 1.0. CXL 1.1 and 1.0 was based on a single node. What CXL 2.0 does is it enables resources to be pooled across multiple nodes. So essentially CXL 2.0 enables us to move from a single node level or a drawer level to a sub-rack or a rack level consisting of multiple nodes in the system. This is shown in the diagram on the right hand side. So you've got multiple hosts that are accessing to a pool of memory through a CXL switch. And that pool of memory can be dynamically assigned to different servers depending on the need. And CXL 2.0 also defines a standardized fabric manager to orchestrate this resource allocation across multiple hosts. Now, instead of the pooled memory, you can also have pooled accelerators on the right side that each server can have access to. So whenever you need, fundamental idea is that whenever you need these resources, you go access those resources. Once you're done with that, you release them, and they basically follow the hot plug flows. CXL 2.0 also architects persistence flows in order to work seamlessly with fabrics. It defines software API for devices to enable system software to manage the devices. We have done security enhancements on top of the device TLB, things like device authentication, link encryption, security through the switches. Fundamentally, CXL 2.0 is a game changer. It enables construction of disaggregated system to improve resource utilization in order to deliver significant total cost of ownership or TCO and power efficient performance improvements in the data center. Now we'll talk about our implementation of CXL microarchitecture, talk about its latency and also some of the bandwidth efficiency numbers. CXL 1.0, 1.1 is implemented in our Intel's Sapphire Rapids CPU, which is a pre-production CPU. And the Sapphire Rapids silicon has been extensively tested with Intel's FPGA, which implements CXL at by 16 running at 32 gig. Now, in addition to our own FPGA, there are several other companies that have announced their CXL implementation interoperating with our Sapphire Rapids silicon. This demonstrates the robustness of the specification as well as the ecosystem's successful adoption ramp. We have done functional verification in our Sapphire Rapids based system, fundamentally doing trillions of transactions every day on the link to stress the traffic flow across different protocols, including all the different conflict cases, one of which we saw. We have also been able to validate the latency and bandwidth expectations. The picture on the left is an IP level microarchitectural block diagram. Our IPs support industry standard interfaces such as PIPE, LPIV, and we have pre-specification versions of CPI, SFI because those implementations predated when we released the CPI as well as SFI specification. The measured latency is provided on the right-hand side along with a very detailed, diagram of each and every one of the components. Things like, you need to byte align, sync header bypass, elastic D-skew buffer, scramble, degrading logic. You can see all the bypass logic there in order to get to the low latency, deframer, framer, credits, it goes through the entire stack there. And the measured latency is 21 to 25 nanosecond, which is consistent with the other IP vendors that have independently reported the latency. So what that means is that the spec defined latency targets of 80 nanoseconds pin to pin for a type 3 access to DRAM or HBM, or for example a snoop to response latency of 50 nanoseconds pin to pin, those are all achievable. It also means that the load to use latency with CXL type 3 devices would be in the 150 to 175 nanoseconds range, which is basically one NUMA hop distance away in an SMP system. Now let's talk about the bandwidth efficiency. The raw bandwidth for a by 16 link at 32 gig is 64 gigabytes per second per direction. That is basically simple multiplication. Now the efficiency with the phi and the flit overhead is 0.924 or 0.939 if you did the sync header bypass, and the way I derived that is shown in the two sub bullets below. For the phi, basically it's the 128 130 encoding, and then we also have to take into account the once every 375 blocks that we use for clock compensation. The flit overhead, as we know, is 64 over 68, and that's 0.924. And if you multiply those are 0.924, and if you did the sync header bypass, you get 0.939. Now, what that means for CXL.io is that the bandwidth is going to be 6% less than the native PCIe 5.0 bandwidth because of the flit overhead. The 64 by 68 is what is going to cause the bandwidth inefficiency, additional inefficiency. Now, we derate that for DLLP, framing, LCRC, header overheads, and it's also payload dependent. How big is the payload size? There are three categories in the .io. One of them is 100% read, the other one is 100% write, and the other one is a 50-50 read-write mix. And we measure the bandwidth efficiency, and as you can see, as the payload size increases, the bandwidth efficiency asymptotically approaches 1, which is what you would expect. Larger the payload, the better the efficiency because your overheads are correspondingly amortized better. Now, looking at CXL.cas and CXL.mem, let's take a look into how we calculate the bandwidth efficiency. For the read in the D to H direction, it's a read current, and similarly for the H to D direction, it's going to be data with the header. So which is basically 24 bits for the data header, and 4 of them we can pack in one 16-byte slot. So if you did the bandwidth calculation, the H to D direction will dominate. So you're going to get 16 by 17 times 0.94, which was the efficiency from the previous slide, times 64 is you're going to get 56.6 gigabytes per second of realizable bandwidth. You do a similar calculation on the right side, the sets of transactions are given there. It's a lot more handshake to do the write. You have to request the data, get the data back. You have to then do the write back, get the completion back. So that efficiency is lower, and as a result, you get 40 gigabytes per second. And depending on the read-write mix, you're going to end up between 40 to 56 in each direction, right? These are two different directions. So you're going to get, on the right side, you're going to get 40, and on the read side, you're going to get about 56.6, but then there will be some overhead because of the write needing the completion on the other direction, on the host to device side direction. CXL.mem, this is where the S2M dominates in the 100% read case and the M2S dominates in the 100% write case, as you would expect, right? Because if you're sending a request in one side and data is coming on the other side, then the side that is doing the data is the one that will be dominating the bandwidth. And here we go through an example calculation with different parameters of 100% read, one write, two read, one write, and you can look into the bandwidths that we get for the different devices. Normally the type 2 devices has less bandwidth efficiency than type 3 because there is an additional NDR response, which is the completion that we have. So the paper goes through the calculations in a lot of detail. You may want to take a look into that. In conclusion, CXL is gaining wide traction in the industry with more than 200 members in the CXL consortium. Several products have been announced with working silicon, very stable silicon. Lots of interoperability announcements at a silicon level is coming out. CXL 3.0 specification just got released. We doubled the data rate to 64 gigatransfers per second. And most importantly, we added a lot of fabric capabilities with full backwards compatibility, including global shared memory. A lot of new capabilities have come with CXL 3.0. The load store IO journey, interconnect journey, it continues to grow strong, both from speeds and feeds capability point of view, as well as from the reach from beyond the node to the rack and beyond level. And it's an exciting journey. Join us if you have not done so. For more details, you can look in on CXL. You can go to the Compute Express link webpage. And with that, thank you very much.
Thank you so much, folks, for listening. So while I'm sharing the new video presentation for the next talk, so the next talk is an invited presentation from Nhat Nguyen of IL Labs. So let me quickly get the video. Okay, before I start the video, a brief bio. So Nhat Nguyen received BS degrees with highest honor in computer engineering, computer science and mathematics from Portland State University, and MS and PhD degrees from UC Berkeley. He was with Hewlett Packard working on RF circuits in silicon bipolar technology, and with Micro Unity working on analog circuits for graphic processors. From 96 to 2020, he was with Rambus, working on high-speed and low-power serial links and I/O interfaces for networking, compute, and memory applications. And since 2021, he has been with IL Labs as Senior Director of Solutions Architecture, working on in-package optical I/O solutions for cloud, HPC, AI/ML, 5G, and in edge. He has published one book chapter and authored over 30 journals and conference papers and holds 30 US patents. His current research interest includes multi-level serial links, optical communications, PLL and CDR designs, clocking architectures, memory interfaces, and wideband circuits. And Dr. Nguyen was a past associate editor of IEEE Transactions on Circuits and Systems, and also an adjunct professor at San Jose State University from 2018 to 2021. So let me start the video, and please let me know if you are not hearing the sound.
Hello everyone. Thank you very much for being here. My name is Nhat Nguyen. I am a Senior Director of Solutions Architecture at IR Labs. The title of my talk is Disaggregated System Architectures within Package Optical I/O for HPC and AI ML computer systems. I would like to thank the Hot Interconnects organizers for this talk invitation. I will go directly into the presentation. This slide shows a conventional system architecture versus a disaggregated system architecture. Disaggregated architectures decouple memory from processors, accelerators, and storage to enable flexible and dynamic resource allocations at either the chassis or rack level. This trend is catching on in HPC for need of larger and configurable memory footprints for HPC AI applications, and in cloud for solving the stranded DRAM. To realize this vision, the fabric connecting these resources together needs optical I/O interconnects. The IR Labs Terrify Optical I/O will be discussed in this talk. This figure shows this disaggregated architecture in HPC computer systems in more details. The left side shows GPU and CPU hosts with their own local memory. The right side shows pools of memory modules, which can be shared with the GPU and CPU hosts. What are the benefits? Increase in memory capacity for the computer nodes, leading to larger and faster analytics and AI training models. And significant application speed up, since the hosts can share the same memory pool. There are challenges to realize this system, however. Among them are the channel reach, power, latency, and bandwidth densities. All of these demands place tremendous difficulties on electrical I/O interconnects. With a WDM optical I/O interconnect, such as the Terrify, these problems can be addressed. I am showing here an example of an HPC computer system. This is the El Capitan supercomputer built for the TriLab. There are multiple cabinets or racks. Each cabinet has 8 chassis. Each chassis has 8 computer plates and 8 switch plates. As shown in the next slide, each computer node has 4 GPUs, 1 CPU, and local memory. The question we want to ask is, can performance be enhanced with additional pools of memory modules? To answer this question, we first analyze the computer node for memory bandwidth and memory capacities. The left side shows the architecture of the El Capitan computer node. Each GPU has 8 HBM memory stacks for a total of 25.6 terabit per second of memory bandwidth. This is a tremendous amount of bandwidth. The memory capacity, on the other hand, is limited, on the order of only about 128 gigabytes. The CPU can provide an additional 512 gigabytes of memory capacities. The 4 GPUs can talk with each other. In order for the GPUs to have access to the main memory associated with the CPU, 8 interconnect links are used. Since each link is a byte 16, these 8 links add up to a total of 128 lanes connecting to the CPU. A key takeaway: the GPUs have very large local memory bandwidth, but very limited capacities even when connecting to the CPU. This will limit the overall performance, system performance. To increase the memory capacities, we can use disaggregated architecture to connect the computer nodes to external memory, as shown in the next slide. Two architectures are shown in this slide. Connecting the CPU to TeraFi optical links is shown on the left side. Here we repurpose 50% of the 128 CPU lanes for optical interconnects, so 64 lanes. The CPU is now co-packaged to a TeraFi optical transceiver. Each TeraFi chiplet has a fan-out of 8, each fiber carrying a bandwidth of 200 gigabit per second, or 8 times 25 gigabit per second. Each TeraFi chiplet has a bandwidth of 1.6 terabit per second. The optical bandwidth is the same as the electrical bandwidth, which must be the case. The capacity improvement in this system can be shown to be at least a 2 order of magnitude better. The architecture on the right side connects both the CPU and the GPU to TeraFi optical links. This architecture assumes that optical I/O links can be added directly to the GPUs. This architecture allows for significantly more improvements in both memory bandwidth and memory capacities. Another key takeaway: the TeraFi in-package optical chiplet is a key technology enabler in these disaggregated architectures. This slide shows a solution to the stranded DRAM in cloud applications using disaggregated memory appliances with optical I/Os. Each computer node is given a configurable amount of memory. Additional memory capacity is added to the system only as needed. So this is good for TCO, or total cost of ownership. The optical links allow the CPU compute nodes to have access to 8 memory appliances on the right-hand side. Each memory appliance has 8 memory modules. Each module in either the E3.S or E3.L form factor. The switch in the middle allows each computer node on the left side to have access to every memory module on the right side. The total memory capacity in these 8 memory appliances are on the order of several terabytes. I went over the system architectures using TeraFi optical chiplets. These slides introduce the TeraFi optical chiplet in more details. It is a fully integrated electro-optical wavelength division multiplexing, or WDM, transceiver chiplet. It has 8 microring modulators. In this particular implementation, the light source was delivered to the rings using the vertical grating couplers. The chiplet was demonstrated at 16 gigabit per second modulation rate, although the operation frequency can go up to 32 gigabit per second. The optical chiplet contains 8 optical ports. with each port having 8 lambdas. When the ring is modulated at 16 gigabit per second, 1 terabyte chiplet can deliver a bandwidth of 1 terabit per second. At 32 gigabit per second rate, the chiplet bandwidth is double to 2 terabit per second. The entire chiplet consumes less than 5 picojoule per bit and has a latency at less than 10 nanoseconds. These are performance metrics that make this disaggregated memory system viable and possible. More details on silicon results for this chiplet can be found at this year's VLSI Technology and Circuit Conference. Also disclosed in this VLSI paper, an Intel Stratic 10 FPGA integrates 5 terabyte optical chiplets in a multi-chip package, or MCP. The electrical interface between the FPGA core and each of the terabyte chiplets is a parallel AIB. The channel length is limited to between 1 to 2 millimeters. The channels are EMIB interposers. The picture at the top corner shows a PCIe card containing 1 Stratic 10 FPGA with 5 integrated terabyte chiplets. You can see the fiber ribbons being routed to the faceplate of the PCIe card. Using a modulation rate of 25 gigabit per second, each chiplet can deliver a bandwidth of 1.6 terabit per second. So 5 such chiplets add up to a total of 8 terabits per second as shown in the slide. I now end the talk with some conclusions. Disaggregated architectures with optical I/O hold the promise of supporting next-generation AI ML workloads and solving the stranded DRAM in cloud applications. Multi-terabit per second optical I/O chiplets are here. We need an ecosystem to align on the roadmaps, using UCIe, CXL, and CWW MSA standards. Terabyte in-package optical I/O is a key technology enabler. And terabyte optical chiplets are being integrated into customers' system. So please stay tuned. With that, thank you very much for listening to the talk.
All right, thank you so much. I would like to first thank the speakers and then the audience, of course, for your patience while we dealt with some technical issues. But I hope that this has been a good technical session, and we look forward to see you in the next session. So thank you so much. Goodbye.